All right, good morning, everyone. If you could begin finding your seats, we're going to get started. All right, good morning. Thank you all for coming. My name is Tim Berkman. I serve as the director for the Macatawa Area Coordinating Council, and on behalf of the MACC, I want to welcome you all here today. Thanks for coming to our annual Watershed meeting. It's great to see you all here. A couple of things just to get started with by way of introduction. Staff that we have here present from the MACC, Kelly Goward is our Watershed project manager and largely responsible for pulling a lot of this together today, so thank you, Kelly. Rob Vink in the back is our agricultural technician, works with a lot of the farmers in the region and promoting and enhancing water quality. We have a few of our policy members here today. David Van Genhoven is our chair here in the second row. I think I saw Mayor DeBoer come in from the City of Holland, Jim Story, Allegan County Commissioner, and who else? Terry Hoffmeyer, Laketown Township. And yes, thank you, Bob Janetsky with the Allegan County Clerk's Office. And then Joe Bush is also here, Water Resource Commissioner for Ottawa County. So thank you all for coming. You know, when Kelly asked me to kick things off, I did this a couple months ago right after I started for our Green Infrastructure Seminar. And I started by telling a few engineer jokes for the engineers of us that were in the room. And this time when she asked me to kick things off, she said I had to be very, very brief and stressed that a few times. So I don't know if that's connected at all or not, but I did not prepare any jokes today. And actually the internet is very devoid of any water resource jokes. So if you have any, put some out there for next year. A couple other announcements though. This meeting is being recorded, so videos and presentations will be posted to our website afterwards if there's something you'd like to follow up on or share with someone. And you will actually, other than right now, not be hearing from MACC staff today, but please pick up a copy of our annual Watershed report that's available in the back and ask us with any questions you may have on it. The agenda is tight though, so we're going to get things started. There's not a lot of time for questions. Kelly's going to keep us on task and moderate things from here on out, but we'll try to keep things moving and stay to our timeline. So with that, I'm going to introduce the first student presentation, the bioaccumulation of cadmium and lead in channel catfish and yellow perch in Lake Macatawa. Andrew, Annalise, and Cleveland.
All right, good morning. Thank you guys for being here. Like you mentioned, we're doing the bioaccumulation of heavy metals in channel catfish and yellow perch, Lake Macatawa Watershed. Andrew Klein, Annalise Sala, Cleveland Tarp. Oop. There we go. All right, so targeted area of study, like mentioned, is the Lake Macatawa Watershed. Targeted species that we looked at is channel catfish and yellow perch. So why we looked at these species specifically is they're one of the most frequently caught game fish in Michigan. They're also one of the most commonly consumed. So we thought that was kind of relevant to our study. Also, there's not a whole lot of actual data that has been gathered about the bioaccumulation potential in these species, so we thought that would be kind of interesting. And the ease of access makes it easy for us to catch, so we can catch a lot of them, so we can have a interesting sample size. Also, they're active all year round, the perch are, so a lot more people are going to be catching them, a lot more people are going to be eating them throughout the year. If we can get this guy to work. Oh, there we go. All right, so heavy metals. How do they actually get into the fish? So usually there's an anthropogenic source of some kind for these fish, for these heavy metals to get into the ecosystem. We'll talk about that in a little bit. But typically it's the bioaccumulation of these heavy metals in organisms. So it starts on a pretty basic level. Really small microorganisms pick up heavy metals. They bind to the muscle tissue actually, and they don't really break down. So they just kind of keep in the muscle tissue. So smaller organisms get eaten by little bigger ones, which get eaten by larger ones, which get eaten by fish, which get eaten by bigger fish, as you can kind of see in the graphic there. And it just slowly begins to kind of accumulate more and more at higher concentrations in the larger animals. So the larger the fish, the larger concentration of the heavy metals. So here we go. If we can get this guy. Oh, there we go. So heavy metals, let's talk about those a little bit. Are they dangerous? Probably. There's been a lot of data about it. The most susceptible people are pregnant women as well as children. It disrupts a lot of vital organ functions, so a lot of kidney failure and stuff like that, and really just horrible, horrible health implications can come from consuming a lot of these heavy metals. So much, in fact, that in the 80s and 90s, there was some legislation that was passed, the lead and copper rule in 1991. That's more looking at or focused on drinking water, but they still took into account that these consumptions of heavy metals is dangerous, so they decided to do something about it and pass this lead and copper rule to try to minimize overall consumption for the general public. There's also, as you can see on the bottom, some WHO and FAO concentration levels for heavy metals in fish. The specific ones that we are looking at is an increased concentration starting with cadmium, and then lead, copper, and then lastly, iron. I don't think I'll ever figure this out. There we go. All right, so some potential sources that we think that where these heavy metals can come from. A lot of them have to do with agricultural runoff. So for a lot of these heavy metals are needed in plant growth, so a lot of fertilizers happen to have them in there. So large storm events happen, a lot of fertilizer comes off, gets put into the Lake MACC watershed. Also, a lot of fossil fuel burning can pollute the air, which then atmospheric deposition into the lake itself can occur, which is a pretty interesting way for heavy metals to get into the ecosystem. And specifically, if we look at lead real quick, so marine paint and anti-fouling paint. We have that a lot with our local area. There's a lot of concentrations of boats near marinas. So anti-fouling paint has a lot of lead in it, actually. So where that concentration of boats are, there's going to be a higher concentration of lead as well. And at the bottom of the screen, we've kind of just listed a few possible local sources where we might figure that some of these heavy metals could actually come from. So Padnos was listed, which is a scrapyard right on the lake. We may be thinking that some of the, when they recycle the metal, some dust, like metal dust could come up from there and get put into the lake or whatnot. You know, we don't know for certain, but we figured that could probably have some implications of some sort.
So as Andrew mentioned, I'm Annalise, and we also wanted to touch on some of the previous studies and experimentation that was done by other student researchers at Hope prior to us. A lot of their methodology was used to jumpstart our project. And as you'll see on the screen, the names of them there, we just wanted to recognize them. And they also found that lead concentrations were higher in round gobies near marina sites. And we wanted to expand on that and see if we could replicate that data. So we had 3 main project goals, the first of which was to quantify and kind of further this knowledge of heavy metal concentrations in Lake MACC fish species. We also wanted to see if we could attribute those to specific anthropogenic sources in this area as well as the surrounding region. So our sites of study are shown on the screen, and a few things that we wanted to point out was we did not catch any catfish at Holland State Park or Windmill Island, and we also did not catch any perch at a public boat ramp. So a little bit about our methodology. As you can assume, we started off by catching fish. Once they were caught, we filleted them, rinsed them with RO water, and stored them in a cooler until we were ready to use them. And then after that, we placed them in drying ovens for about as long as it took to reach a consistent weight at about 65 degrees Celsius. And following that, we prepared 1 gram samples to be digested. After the 1 gram samples were prepared, we placed them in test tubes, which were then added 10 mils of concentrated 69% nitric acid to those test tubes. And then we added the test tubes to a mineral oil bath, which was the most competent way for us to heat these and ensure that they were all heated to the same temperature. We placed those test tubes into larger beakers that were filled with mineral oil, and we actually used chicken wire to suspend the test tubes in the mineral oil, and so that we could place a stir bar beneath them. Following this, we had to filter our samples because we needed to analyze them using AA spectrometry, which is a machine that if there was any fish tissue left in our samples, it would clog the machine, and it's thousands of dollars, and we would not want that. That's not in our budget. So we put them through 0.45 micron syringe filters to begin with, and then just to ensure that everything was out of them, we also filtered them through Wattman number 1 grade papers, which you can see we did through I forget what that apparatus is called.
All right, so a few of the results we were able to find is we found the average concentration of copper, lead, cadmium, and iron in these samples. And we were able to compare those to the WHO and FAO highest permissible levels. And some correlations we looked for is we looked for correlations with sample location and the fish species. So here's our data. We have our analytes on the left side, the recommended levels next to that, and each concentration is reported with its standard deviation. And all of the levels were higher than the recommended levels, with the exception of iron. And the only significant difference between catfish and perch was that lead was higher in those. So starting with the location, we have on the y-axis the concentration, and on the x the location, and they go from west to east accordingly to see if there's any gradient of concentration, but we didn't see any correlations with that. And these red lines are the recommended levels, so you can see that iron is the only one that is below the levels. All right, now this is the same graph, but for copper and cadmium and perch. Again, all the data was indistinguishable, so there's no trends across the lake. And again, these are the recommended levels, and both are above them. And in terms of iron and lead, we divided these samples into lake sites and river sites. The river site was the river behind Windmill Island, and we did that because the average concentration was lower in Windmill Island than the other sites. You can see that once I put this line in here. For lead, we actually didn't find any in the perch behind Windmill Island, and then in the lake they're exponentially higher. So I guess just some conclusions we had is we did find detectable limits or levels of lead, copper, cadmium, and iron. Lead, cadmium, and copper exceeded the recommended levels, and lead and iron were lowest at the Windmill Island site. And future work would be to obtain a larger sample size and would be to analyze the sediments and water samples around them to see if there's correlations with that.
We'd like to acknowledge Dr. Ed Hansen, Dr. Brown, and Dr. Piper, for all their advising through this process. We'd also like to thank the Hope College Geology and Environmental Sciences Department for supplying us with all the necessary things we needed, and also for the Hope College Chemistry Department for allowing us to use their very expensive machine that I mentioned earlier, and the previous student researchers Nick Blogin, Austin Krehol, and Kelly Kruger. Thank you.
In your work, any ideas when you took your sample size, the area of dispersion around these boat ramps and state park? I mean, your samples were single location, what kind of area?
Yep, so he asked what the dispersion of the fish that we caught in each locality, and to be honest, I'm not really sure. I'm not really a biologist, I'm a geologist, so look more at rocks than fish. But I mean, I would kind of assume that the fish kind of would hang out in like a general area around the locality that we caught. I think that really makes sense when we looked at the Windmill Island example where there was no lead whatsoever in those fish, yet in all of the lakeside fishes, there was they all had lead in them. So I figured they weren't probably swimming up the river and around they kind of stay in their own little neighborhood of sorts. But
And then your samples for you took some bottom sediments, right?
we did not. That was on our future work. We said if we did more, if we had some more time, we would like take cores of sediments, analyze those, as well as the water as well. Any other questions?
My perception is that people are fishing a fair amount, like say Cowan Park.
Mm-hmm.
And when I walk through there, I'm usually checking out like the fish myself.
Mhm.
They're catching fish and they're taking them home. And some of these catfish are fairly large and they're
Yep.
eating them. Could we do anything about that? Put a sign up? I mean, what about the health issues of the folks in our community that are eating this fish?
Absolutely. Yeah, so he just asked kind of the health concerns on people that consume this fish. And every time that we went out, pretty much every time we went out, we saw other people that were fishing. And they weren't fishing for fun. They were fishing and putting them in a cooler, and they were putting them in their cooler to go home and eat. Like, that's kind of what I was assuming. And so, like, I was kind of alarmed when we saw the data, and almost all of them exceeded, like, the recommended levels in fish tissue. So I'm like, wow, this could potentially be a serious issue unless we completely messed up our data somehow, which I don't think we did. Like a lot of these people are potentially eating fish that are above the recommended levels of the WHO and FAO, which is rather concerning to me. But yeah. In the back there?
Yeah, do you share your information, say with the county health department or the state DEQ, or are they interested in your results?
Yeah, so we asked if the DEQ was interested at all in our results, and I don't even know, we literally just put this presentation together a couple days ago. Like, we're just finishing up this project, but if people was interested in our data, like, I would be interested to share this because I think it's kind of pertinent information to the local community.
Do you have any theories on why the Little Island Garden area is no lead?
Yeah, so she asked if there was any information if we knew why there was no lead with the Windmill Island. And I think because the previous study that we looked at for our paper in 2013, I believe, they looked at just lead, right? So they looked at the concentrations of lead near marinas, which is where a lot of boats are. And a lot of marine paint, like a component of it is lead. So a lot of paint on the bottom of the boats actually contain lead. So over time, if you have a lot of concentration of boats, you're going to have an increased concentration of lead in that water, in those sediments, in those fish as well. And that was kind of something that other project explored in their presentation of their project.
Okay, and with that, I'm going to have to cut off questions so we can move on to the next presentation. We will have a little bit of a break at the end of the student presentation, so you might be able to catch up with a few questions.
All right, thank you guys so much.
Where'd Sandy go? There you are. Sorry, I couldn't find my partner. My name is Sandy Brookhouse. I am actually a non-traditional student at Hope College, and these are my lab partners. This is Caitlin Kaltrider and Samuel Click. And we are here to present to you our research on vermiculite and hugelkultur and how they can remediate urban runoff. So let me see if I can navigate this. I'm sorry. So we chose for our project, we wanted to do something with urban runoff just because of the more recent concern in recent years about the environmental effects, and we wanted to do something related to that. Where do I point this to get it? Okay. There we go. As a group, we had three concerns. We wanted to know, is there a way to work with nature to remediate runoff? Are there alternatives to taxation? We know that some states are starting to tax based on the percentage of impervious surface on a property. And what about if you can't get rid of your impervious surface for some reason? Is there an alternative? Is there a way to remediate your runoff and slow it down so that yours is not running off? And we were also concerned about the soils and what's happening to the soils when things run through them. So we started with our original question being to do with runoff contamination on previously engineered soils. And we chose, as our previously engineered soils, the backyard of my house. It was an easy location. So the blue areas by the house represent areas that have been extensively had hugelkultur applied, and hugelkultur is a method of burying wood underground just about a foot under the soil so that you can harvest and store water, but you can, and then you can grow things on top, which is what I've done in my garden. And this has worked really well for me, just for watering purposes. I've greatly reduced my watering through the year just because I have my water underground waiting. So we wanted to work on this, and we decided we better have something other than just hugelkultur, and we decided would like to work with vermiculite. We'd like to know how it, is it possible to remediate runoff with vermiculite? It's a highly absorbent clay mineral, and maybe it could absorb some of that runoff before it just runs off, and give it a chance to maybe store the water and maybe let it do something to help our groundwater. So with that, I would like to give it to Caitlin, and she'll tell you how we did it.
Oh, sorry. Okay, so first of all, we took 2.5-foot columns, plastic columns with filters on the bottom, and we filled them with the hugelkultur matrix or the vermiculite matrix. And we did an initial run through to determine how long it would actually take for water to filter through. Then, after this, we decided to break apart the hugelkultur and vermiculite to reduce pore space and increase surface area. So from there, we constructed our physical columns, which included 300 milliliters of the matrix for the vermiculite, and then for the hugelkultur, it contained 900 milliliters, 300 being the B horizon, 300 being the hugelkultur, and 300 being the A horizon. From there, columns were hung from a ring stand, and a drip apparatus was placed into them, which consisted of a funnel attached to a rubber tube with a titration pipette tip. This allowed for us to drip our concentrated solutions through, increasing the runtime, increasing contact of the solution with the matrix. From there, we made our concentration solutions. They were 10 ppm copper, 15 ppm lead, and 5 ppm zinc. And then we completed 3 trials of the pour-through for both hugelkultur and vermiculite. Once the pour-through was complete, we filtered the samples. So we took the pour-through, what was left from pouring through the matrix, and we ran it through filters to reduce any particulate matter. They were 0.45 micron syringe filters. And then we created standards using serial dilutions from our stock solutions, and we ran those through the atomic absorption spectrometer. And from there, we calibrated the AA, and we used the following absorbance settings for each metal. The absorbance settings help to detect the certain metals, and once everything was run through, the results were recorded.
All right, so we're going to talk a little bit about this calibration that you were just saying. So on the left side of the column, it might be a little small, but it's all right. We'll give you the gist. You've got the concentration of the standards that we made, so we know those concentrations. And then on the right side of that table, we have the absorbances. So we use those two values to get this graph, which is a relationship between the two. And from there, we can learn more about what we have running through our columns. So, so here's where we use that data. So for our control solutions, we'll start there in the upper right-hand corner. We have controls for, we ran it through the vermiculite and the soil, and for each one of those, we tested for our lead, our copper, and our zinc. So as you can see, those values of the absorption kind of range from about 0.000 to 0.038. So there are two options. We could have slightly contaminated soil and vermiculite. I think the more likely option is that we're at such a fine quantity that we're nearing the detection limit of the machine. So leading to our other results here. So each one of those, we have an absorbance, and we use that relationship you saw on the previous graph to relate that to a concentration. So, and once again, we'll talk about this a little more in the next graph, but we have our lead, we have our copper, and we have our zinc for each one. And here's where you can really see the results. So these big blue bars are our initial concentrations. That's what we poured into the top of the column before it was treated at all. And those little red and gray bars that you can hardly see are what came out of each of the columns. So we're seeing a drastic reduction, in some cases about 99%. And if you can see closely, you'll see that we actually have negative concentrations for a couple of those, which don't actually exist. So what we're seeing there again is that although we're not able to say exactly what those concentrations are, we're seeing that they are being depleted to a point where we can almost hardly tell that they're there. So, which is really good for our study, and we're really surprised to see that it was this effective. If you look at the yellow bars, those are the recommended concentrations from the EPA. So you can see that our systems definitely bring down that contaminated solutions to a safe drinking level. And a couple other sources of error. If we were to do this again, we would have liked to change the range of our calibration curve. We had this big range from about 0 to like 60 parts per million. And really, as our results showed, we're working in the 0 to like 0.5 parts per million. So I think we could get more accurate results if we calibrated differently. And also something interesting, we found a lot of organisms in sandy soil. So we have no evidence to show that they affected our trial at all, but it'd be interesting to see if these millipedes and worms are having any effect on the uptake of our heavy metals.
So in conclusion, what we based on our promising preliminary analysis, we recommend that there would be further testing on vermiculite and hugelkultur to find out how they work in remediation of runoff contaminants. We, excuse me. I'm still not able to do this without notes. Oh, thank you. And as for what's next, we'd really like to see some field testing of vermiculite and hugelkultur. How well do they absorb? Could we contour the ground? In my yard, I've contoured the ground so that it all points towards the hugelkultur to store it there. Can we contour, maybe in urban environments, can you contour the ground and point it towards something so that you can absorb some of that underground and maybe remediate some of that runoff? We'd like to see field testing with that and with vermiculite and just see kind of, maybe we could mix them together, we don't know. But could more be done to remediate the runoff? We'd like to know more about the soil. We've only done just a very few of these. We'd like to do enough tests that we could work out our instrumentation and make sure that those small numbers really are what we think they're supposed to be. And we'd like to know how the different soils work together, how the vermiculite works, what would happen if we did different grain sizes, because we did a lot of artificial stuff in the lab since we weren't able to. I forgot to mention we were originally going to use the runoff from my roof, and I didn't have any contaminants, which was a good thing. So we had to go to the lab. That was why we ended up in the lab. So because it's a lab test, we had to do some things that were pretty artificial. So we'd like to do some more with that and then find a way to do it on a larger scale where everything didn't have to be so artificial. And there are sources, and are there any questions?
We've got about 4 minutes for questions. You guys are spot on.
Would you expect the effect of the filtration to diminish over time?
The question was, would we expect the effect of the filtration to diminish over time? I would expect so, but I don't know. I mean, one of the other groups did an experiment with plants and how they draw out of the soil. I'd love to see how you could combine the two. I would expect over time, yes, the filtration would change. So.
Yeah, so I think part of why this works so well is because we had much more hugelkultur and vermiculite than we needed. So we weren't saturating. There were still spots where it could adsorb to the surfaces of the soil matrix and the vermiculite. So that's a very good question. Thank you for addressing that. Any others? Yeah, in the back.
In your investigation, you were talking about whether, future research of whether the worms and the millipedes that are affecting that. Did you have any kind of an inventory of the microorganisms that were in there? Did you take any kind of inventory of that?
Not specifically, other than what we visually observed, just like pulling the stuff out of the column. As you saw the picture with the worm, we saw quite a few little millipedes, but as far as a biology inventory, we didn't do anything to that effect. Yes.
The technique of hugelculture materials, where is that practiced at, and what kind of wood materials are you, is used in that?
Okay, the question's about the logistics and the locale of where you would find hugelkultur. It's a lot of the Permaculture Institute uses hugelkultur. I don't know exactly where it originates, and if you go on the internet, you can find all different varieties. It comes in all shapes and sizes, but for the most part, you want older wood. You want to put it in the grounds because it's real absorbent. You want softer woods, not harder woods. It's just, my hugelkultur is harder wood, a little bit younger, but other people's, it's just real varied. So a lot of people do it when they're doing like urban and organic gardening and stuff. So, anybody else? Yes.
Can you say anything about how much water these materials can hold and how fast the water will flow through them?
Yeah, that's a good question. How much water can they hold and how much water can flow through them? There's a limit probably to both, obviously. We did pre-saturate our columns. We don't really know that, but we could find that out with further testing. Unfortunately, we are all getting ready to start a new semester of new things, and so we won't be doing that, but we'd like to see an answer to that question, obviously. So.
Thank you.
Hi, everyone. Thank you for being here today. My name is Alexandra Donaldson. This is Ian Jorgensen and Jared Jan. And our research project was focused on heavy metals in drinking water and in soil on and around Hope College's campus. So our research project had two parts. The first part was a survey of the drinking water on Hope College's campus. And I'll hand things over to Ian to explain.
All right, so why, heavy metals in drinking water? It's been, somewhat of a hot topic in the state of Michigan the past decade, specifically talking about Flint and their water crisis with the presence of heavy metals due to corrosion of their public piping systems. And we wanted to take a look at Hope College's drinking water to see if there were any, or there could be a chance of any similar problems going on.
So to go about this, we specifically looked at Hope's campus. There is a map on the screen. We tried to go in as many buildings as possible. So like DeVos Fieldhouse is number 10, I believe, and that was important just because like a lot of people attend games there, basketball happens, so a lot of water would be consumed. But we also wanted to look at like newer and older buildings. So like the Boatman Student Center was just built and opened a couple years ago, where like Chapel, Graves, and the library are a little bit older. So we just wanted to try and get a wide range of buildings that are found on campus.
Yeah, so our sampling procedure for this project, ideally we're looking at the water fountains in the buildings on campus because that's obviously where the water is being consumed from. So our sampling process involved taking water samples morning and night at 8 a.m. and 8 p.m. with a 12-hour interval in between just to see possibly if there was any changes throughout those 12 hours. And so we sampled, of course, the same water fountain each time. And our samples were collected in 500 milliliter Nalgene plastic water bottles that were properly cleaned to remove the presence of any trace metals that could be in there. And once collected, our samples were stored in a cold refrigerator to prevent the growth of any microbials or anything like that. And as you can see on the screen, there's a picture of just an example of what one of our
bottles, what their label looked like with the location of the sample, the time that it was collected, and the date that it was collected.
So for testing, we wanted to determine the concentrations of lead and copper that was in the drinking water at Hope College. And we were able to use atomic absorption spectroscopy, the really expensive machine that was mentioned earlier, same one. So what we wanted to do to begin with is just determine if there were any detectable levels at all in the drinking water. So it's a bit less precise, but it does tell you if there's anything at all. And if there were detectable levels of these, of lead and copper, we would then move forward with more precise and more exact testing with the same machine and a calibration curve to determine the exact concentrations.
And so these are our results. We sampled on 2 different days with a total of 20 samples. So that's about 10 drinking fountains total. As you can see, there were no detectable limits in any of our samples when we did the preliminary run-through. That's really good for Hope College, but for our project it was slightly disappointing just because it's not very eventful. But that will lead into the next part.
Yeah, so as Jared just mentioned, there were absolutely no detectable levels of lead or copper in the samples that we collected. So again, this is good for Hope College, but we decided after this to do a different part to our project. But yeah, so we can safely say that the drinking water on Hope's campus is free of lead and copper and safe for consumption.
So yeah, after we saw this, we decided to kind of pivot the focus of our project a little bit into part 2, which is just leachable heavy metals in the soil on and near Hope College's campus, specifically looking at the construction area around the Western Theological Seminary Library.
And we still want to tie in the drinking water to the project in a way as much as possible. So we had heard that there was corrosion going on at the Western Theological Seminary's library. Whether it's just the building overall or the pipes, we weren't exactly sure. But we wanted to test and look to see how that could affect the overall area. So we looked specifically at the soils that we found at the construction site.
Yeah, so as Jared had mentioned, we sampled native soil from the construction site, 1 sample from the back of the construction site closer to Hope College's campus, and 1 sample from the front of the construction site on 13th Street towards the front of the building. And both of those were native soil samples, so we made sure that we weren't getting any outside soils that were brought in for the construction process.
So once we had the soils sampled, they were stored in a cold room overnight until we were ready for extraction and digestion. And the first step of the extraction process is to determine the pH of the soils after their reaction with hydrochloric acid. And the main goal of this first step is to determine the extraction fluid that we would use to leach the heavy metals out of the soils, which ended up being a mixture of acetic acid, sodium hydroxide, and water. And once we determined that, 100 grams of the soil was placed with the fluid and in an agitator and shaken overnight to promote leaching of these or any heavy metals that may be present from the soil into the fluid. And once that was completed, we took 100 milliliters of each sample's fluid and digested it down to 50 milliliters, and we were ready for analysis after that step.
So like the water samples, we did the preliminary run-through just to see if we had any detectable limits of heavy metals, and we did find zinc, copper, lead, magnesium, manganese, nickel, and iron. And after doing a little bit of research, we decided to focus more on lead, copper, and iron to look at those exact levels, because those are known to be indicators of corrosion, and those could potentially affect human health.
Yeah, so these are the results that we found after our analysis of the fluid. And so the F1, 2, and 3 represent the trials of the samples that were collected from the front of the construction site, as previously mentioned, and B1, 2, and 3 represent the trials of the samples that were collected from the back of the construction site. And as you can see across the board for copper, lead, and iron, we're having higher results from the samples in the back of the construction site, and we think this possibly could be due to heavy traffic of machinery that could be, contaminating our location and such.
So these are the maximum contaminant levels for our 3 heavy metals that we tested for. for soil and drinking water respectively, according to the EPA. And as you can see, we really didn't come close to the contaminant levels for soil, but as you can also see, all three levels are above the recommended, or the maximum contaminant levels for drinking water. So what does this mean? Our project kind of simulates how groundwater would leach out heavy metals from a soil. So groundwater wouldn't exactly have the same standards as drinking water, obviously. So I believe that a simple treatment process would be able to mitigate the minimal amount of heavy metals that are present in any water that could come in contact with this soil. Okay. So our soil samples did not exceed the maximum contaminant levels for soil, but the very presence of copper could cause a problem for an ecosystem. Water-soluble copper compounds could enter the groundwater, and copper that enters groundwater could potentially collect in the sediments of lakes, rivers, and estuaries, which could be some, future work that you would want to do in conjunction with a project like this. And also, the heavy metal concentrations were higher in the back of the construction site compared to the front, and this is an expected result. That's where a lot more construction and movement of heavy machinery was going on.
So kind of to wrap things up, we did find no detectable limits for lead and copper in the drinking water at Hope, so that's great. But they were found in the soil. The levels weren't extremely high and concerning, but it's still important to note. And then we also want to just acknowledge that as long as the correct filtration processes and protocol are put in process, that everything should be okay for human consumption, and they really shouldn't pose a threat to human health overall.
Yeah, so obviously this project could have some more steps to it. And so some of the future work that we would do, if would be possible, we would like to take a control sample of soil from a more neutral site, not involved in construction and where the corrosion process was going on. So we would want to analyze that neutral sample just like we had with our contaminated samples, and just see how those compared, so we could get a more accurate analysis of where these heavy metals were coming from and how they compared to a neutral area.
Yeah, these are sources. We would also like to specifically thank and acknowledge Dr. Kenneth Brown of the Chemistry Department and Dr. Ed Hansen, of course, of the Geology Department at Hope College, for their help and contributions to our research project. So yeah, that's all we have for you today. We're here.
You're part of that back in the middle of the presentation. You said you use pH to determine which filter liquid you use. What was your decision point? What did you decide?
So she asked about the extraction fluid that we used. It was a method suggested by Dr. Ken Brown that's essentially just to be able to leach out the heavy metals that we wanted to analyze from the soil, and it's just a simple process of reacting, or having the soil react with hydrochloric acid, observing the pH afterward, and then using the result there to determine the mixture of acetic acid, sodium hydroxide, and water that we would use to extract out the heavy metals.
So a lower pH you would do what, and higher you would do?
That, it was more, here, you can hand it over to Allie.
So depending on the pH of our sample after it was mixed with the acetic acid, or not acetic acid, sorry, HCl, and heated up, the extraction fluid, if it was going to be a pH over 5, would just be simply a mixture of acetic acid and water. But our reaction, since it had a lower pH, when we added HCl, I think it was a pH of about 1. So then, following the EPA leaching procedure protocol, we used a extraction fluid that also included sodium hydroxide, which the other fluid did not have. Yeah.
Did you have any discussions with the City of Holland or DPW with regards to any chemical additives that they put into the drinking water system to prevent leaching out?
So the question was if we had talked to the City of Holland or the BPW about any chemical treatments that they had put on their infrastructure. And we did not talk to the City of Holland. We saw that they had previously done water surveys, and it came back with a clean bill of health, except there had not previously, I don't think, had been surveys done on Hope College's campus. And so we didn't specifically ask them about those types of procedures at Hope College's campus. But we did ask for their permission to make sure that it was okay that we were doing this, and we got the all clear. So, yeah. Yes.
I think Dave Prosser last night from the DPW mentioned that our water source is non-corrosive and therefore the metals don't leach. And so we're kind of blessed with our source.
Mm-hmm.
In Holland, in over 12 years, they've tested every 3 and they have 0.
Yeah, that's good news. We're glad we have that on Hope College's campus, too.
More questions?
No, just that we've heard a rumor that someone had done this a couple decades ago and found detectable amounts in drinking fountains in the morning. And if that was true 2 decades ago, it's not true now.
Yeah.
Hello, everybody. Thank you for joining us. I am Liam Kleinexel. This is Liz Moorhead. This is Jacob Stid, and we're all undergrad geo majors at Hope. Today, we're going to talk a little bit about heavy metal uptake in garden vegetables. Just a little introduction and background. I'm sure some of you are familiar with urban farming and how it's become a little bit more of an efficient way to produce vegetables and produce in heavy populated areas, and an effective way to repurpose abandoned urban properties as well. However, there are some concerns with this associated with obviously the urban society and contaminants and runoff, and that's what we kind of wanted to look at. And these contaminants have been a problem and caused some reconsideration for urban farm localities where they want to grow. And this also pertains obviously to other agricultural communities in urban areas that may be affected by stormwater runoff. A little bit further, there's at Cornell and New York Department of Health in 2010, they conducted some experiments looking at contaminants in runoff in urban areas, and they found cadmium, copper, and lead. And a little bit behind those heavy metals, cadmium comes from electric car batteries and acts as a carcinogen in human bodies. Copper comes from brakes and motors and any some other areas in cars, and that can cause kidney and liver damage. And lead's the big one, another carcinogen. A lot of it comes from the legacy lead era, which is thankfully not going on anymore. And the EPA reference doses for these are cadmium extremely low at 0.001 part per million, and then copper at 1.3 ppm, and lead 0.3 to 0.6 parts per million. And the vegetables that we decided to grow for our experiment were spinach, radish, and arugula. And some of the questions that we wanted to pose prior to our experiment and study: is it first viable to grow our selected vegetables in contaminated soils with our selected heavy metals? And if so, what is the amount of contaminant that they might uptake? Secondly, is there a specific heavy metal that we were testing that is more or less prone to being uptaken in our selected plants? Third, what may be the connection and effect between the contaminations of rainwater runoff and the urban settings where they might be located? And lastly, is there a detectable threshold limit for these plants and the heavy metals that they are uptaking? And what might that threshold level be?
So before we started doing our methods, we did a little further investigation on how often it rains and how much rainwater we actually collect. So we looked into the summer months of June, July, and August of 2018, and we found that there was an average of 3.6 inches of rainwater in those months. And with that, there was a significant rainfall every 4.5 to 5 days. So using that, we calculated that each time that we did a storm event on our vegetables, that there should be about 0.4 inches of water in our containers that we used. So that way, after everything was said and done, we had that 3.6 inches of rainwater in our cups. And then that table there at the bottom lists our different metals that we use, so the copper, cadmium, and lead, and then how much concentrations we poured into each individual cup. So for our growing methods, we first got some seeds and some soil and some beds, and we just started to get everything to sprout. And once they were sprouted, we individually transferred a few sprouts into these cups. And then from there, we were able to start a contamination. So you have your individual cup, and you pour some water into it. And that's how we just started. Every time in between a concentration event, we did a water event. And then after the water, we did contaminate the cup with copper, cadmium, or lead in the specific concentration. Each cup was labeled so we knew exactly where each one needed to go. And then this was repeated a total of 6 times over our 4 weeks. And then they were ready to be harvested. So this is what they looked like after those, the 1 week of initial growth in the beds and then the 4 weeks of contamination. This is what we came out with. And then from there, once everything was harvested, we needed to prepare them for digestion so that way we could actually analyze our samples. So this was done by initially just cleaning each individual stem because there was a lot of dirt and grime on them. So we just rinsed them off with water. We took an initial wet weight of our sample, and then they were placed in an oven for 20 hours, and they were dried at 120 degrees Celsius, just so that way we would get a good ashy material, which could be a lot easier to digest. So these were all placed in their individual labeled vials, and we added 5 milliliters of concentrated nitric acid, that's 69% that the fish group also used. And then from there, after they sat for 96 hours over Thanksgiving, we added an additional 4 milliliters of water and 1 milliliter of hydrogen peroxide to dilute them to a safer level. And that finished off our digestion process. They were filtered because we did not want to clog the expensive machine. And then they were put in the most expensive machine.
All right, so I'm going to take you through results, and we're going to start with qualitative results, sorry. So as Liz said, this is the experimental setup. As you can see, you've got arugula, spinach, and radish, and on the right you have the different analytes that we used, and then on the left you have the low concentration plants, and then the high concentration plants on the right, which is where we, for copper, that was 500 parts per million, and then for cadmium and lead, that was 250 parts per million. The next one. So this is an actual image on the 34th day of the trial, and on the 35th day we harvested. And one thing I want to point out from this image is that, as you can see, the copper plants on the bottom, and specifically all of the high concentration plants on the right, had less vigorous growth than the low concentrations to the left. This is obviously qualitative. It's just by visuals. You can see there's less green in those areas on the right than to the left. So now for our AAS, our quantitative results. So this is a graph of copper concentrations. On the y-axis we have the concentration within each of the plants that we harvested, and then on the x-axis we have the concentration of the simulated storm event concentrations that we poured over the plants. So first I want to go back to what Liam said, and the reference dose for copper was 1.3 parts per million, so we're going to draw that line on this graph right now. So that's 1.3 parts per million. So as you can see, radishes and arugula both surpass that threshold for the EPA guidelines for a reference dose, but only at 450 to 500 parts per million runoff concentration. That is a realistic runoff concentration, but it's not very common. I would also like to acknowledge that spinach had a much lower threshold, or much lower uptake than what the threshold was as compared to arugula and spinach. So now on to lead. We have the same axes on the graph. So the reference dose for lead, as you remember, was 0.3 to 0.6 parts per million. So we're going to draw that line in here now. Maybe? Oh, yes, up top. Okay. There's a glare on the screen. So as you can see, it's way off the screen. It's nowhere near any of the uptakes that we recorded. So what that means is that all of the plants that we contaminated and then harvested under EPA guidelines and under the analog that we used, our number of storm events and all that. All of the plants that we harvested were safe to eat. So again, none of the plants contain the threshold, and again, spinach had the lowest uptake relative to the two other plants. So finally, for cadmium, the reference dose for cadmium was 1 part per billion, or 0.001 parts per million. So we're going to draw that line on the graph now. So as you can see, arugula does surpass that concentration at roughly 200 parts per million runoff. And at this point, radish had the lowest uptake as compared to spinach. But I also want to acknowledge that as we go down in the relative concentration range, on the y-axis, our errors do go up. So what does all this mean? So for copper, I would first like to acknowledge that the uptakes fit a second-order polynomial very well with a high correlation coefficient, which means that you can plot these to a line and figure out at what point, for instance, spinach would reach that threshold. Spinach would reach that threshold at 1,300 parts per million copper runoff. That is realistic, as in it could happen. It's not very likely. And then radishes and arugula are both safe to grow under 450 parts per million stormwater runoff. For lead, none of our vegetables reach the EPA reference dose limit, which means you could eat any of our vegetables safely for an extended period of time with no adverse health effects. And for lead, what's interesting, which is different than the other two analytes that we tested, is our graph fits a power regression curve, which means that, as Liam said earlier, one of our questions is, can we find a limit to what these plants can uptake? And the fact that it's a power regression curve means that we very well could, if we extended this graph out as far as the runoff concentrations that we were looking at, we very well could find a limit to the concentration that these plants, these vegetables anyway, could uptake. So I ran the arugula through the power regression equation that fit to the line, and it would be safe to eat arugula up through a runoff of 14,000 parts per million copper. Kind of unrealistic. Possible, but unrealistic. Cadmium, our vegetables were a little bit more sensitive to toxicity. As you can see, they're all relatively close to the threshold, and arugula did surpass the threshold, radishes. And radishes are unsafe to eat at 190 ppm runoff, which is very realistic. Although the nice thing about cadmium is that because it's mostly from electric car batteries, it's the concentration in runoff and in parking lots and such is much less. So what's also nice is that we have a much lower uptake for cadmium than for both copper and lead relatively to both of them.
Some other further applications that you can apply to our study is we can now determine that safe urban locations based on EPA regulations and guidelines. Secondly, garden vegetables do not grow well in soil specifically contaminated with high concentrations of copper, as you saw in the pictures and the data. And third, the methodology that we used in this experiment can be applied and used in urban farm operations in order to determine whether their soil and plants are uptaking heavy metals. And lastly, a big good beneficial thing about this study is it's very cheap and very repeatable.
So if we were able to continue this project next semester or sometime in the future, first and foremost, we would like to start by actually testing real stormwater that we could have found in parking lots to see how our concentrations compared to that and what kind of uptake those proposed. With that, longer growing periods for our vegetables in a different range of concentrations to kind of see if maybe we could find some limits, especially the growth period, because, for example, our radishes, we were hoping that we would start to get small bulbs by the end of our 5 weeks of growing, and we didn't. We just had greens. So we would really like to see if maybe the fruit produced by the vegetables actually had some kind of variation compared to greens. And then we'd like to use a variety of vegetables as well, just not the 3 specific ones that we found grew pretty fast. And then we would like to take accurate wet and dry weights of our vegetables to see if any metal had a specific effect on the uptake of water in the plant and how well they grew. So like, for example, that copper picture that we had shown, are those wet weights of the plants like comparable to what the actual water content in the plant should be, or was it lower or higher? And then lastly, we would like to use an ICP OES for more accurate measurements, especially when it got down to the copper and we had those very large error bars, just to kind of erase that questioning in our mind.
Finally, we would like to acknowledge the Hope College Geology Department for funding this project, Dr. Shorb, Dr. Boltman, Dr. Peterson, Dr. Brown, and Dr. Hawk for advising us through the procedure and instrumentation during the project, and as well as Dr. Hansen for advising us from start to finish. Any questions?
Not to intersect the different projects, but were you, if the vegetables all turned out well, were you concerned about the fish? Have you heard that kind of thing?
Yes, we were. So I don't know how we would exactly correlate those, although theirs was a little more intimidating than ours because we found that most of our plants were below the limits and that it was safe to eat most of the plants under relatively normal conditions, whereas they found that under actual conditions, it's actually not under the recommended guidelines. So that was very concerning, especially coming from a standpoint where what we had was safe and what they had was not safe. So, right, most definitely.
If a resident wanted to test some soils that they have as a garden area,
Yeah.
how could they get the heavy metal analysis done?
So we specifically tested the vegetable. Is that what you're talking about? Maybe
No,
testing the soil.
Soil prior to.
Okay.
You used a known amount. You
Mhm.
did that. But if someone wanted to say, okay, I'm going to do this and look at what the uptake is, not from the water that they're putting on, because they're going to use some of the good water.
But from the soil.
From the city.
Yeah.
They're going to come from the soil.
Yeah. So the question is, how would a resident go about determining what the concentrations of these analytes are in anyone's soil? So we used a plant digestion procedure because we were analyzing the concentration in plants, but there are also soil digestion procedures where you can take soil, digest the soil itself, break it down, remove the organics, and then you're left with a solution of just the heavy metals that you can then also run on an AA or an ICP. You have to have an AA or an ICP, but.
I think likewise, it probably is pretty expensive for anybody in the community, but I mean, we saw that Ian, Jared, and Allie kind of did that with their samples. They were able to test their soil and see what happened. So if somebody maybe got in contact with the college or something and they were very interested and willing to pay for it, maybe it would be possible. Yes, in the back.
What made you choose those specific vegetables?
So the question was, why did we choose those vegetables? We did a little research on Google and we found that specifically microgreens grew pretty fast, and we knew arugula, for example, is very commonly eaten in salads and many other kind of dishes. And that's also a microgreen, so we got seeds for those. And then spinach and radishes were also supposed to grow within a 4-week period. And we figured we don't have too much time to do this project, so 4 weeks seems reasonable. Yes. Oh.
Jim, I'm sorry, I gotta cut you off, but maybe catch him at the break. All right, thank you guys.
Great job to all our presenters. Thank you for your time and efforts in that. So at this point in our agenda is where we give out our annual Stakeholder of the Year for the Watershed. And when our staff got together, it did not take long at all for us to nominate this individual. So since 2001, this is an award that we've given out to a person, an entity, an organization that's kind of gone above and beyond as far as being a strong supporter of the Macatawa Watershed Project and/or has played an important role in promoting and advancing water quality within the Macatawa Watershed. So at this time, I'd like to call forward Rick Bosch. Rick is being presented with the 2018 award to recognize his several years of volunteer work for the MACC and other organizations that are working to improve the Macatawa Watershed. And I've got a list of several reasons why he was a good fit for this award. So starting off with the MACC, he participates regularly in our Watershed Advisory Committee, and we're thankful for that. He volunteers for river cleanups, macroinvertebrate monitoring, road stream crossing inventories, so he's not afraid to jump in the water. He's obtained, scanned, organized, and archived for us historic watershed documents. for retaining that important legacy information. With Project Clarity, he volunteers regularly at the Water Festival. He participates in citizen science, collecting weekly water quality readings at Paw Paw Park. He's reviewed and provided comments on several reports. He definitely goes above and beyond the average volunteer with both his background and service hours. And then with Ottawa County Parks, he's the park monitor and park steward for Paw Paw Park. He's mapped and removed invasive species, has made great recommendations on management, and often puts his own back into the management solutions. He's discovered several new invasive populations, including Phragmites. Additionally, he's potentially found a biocontrol on poison hemlock, one of the park's worst invasives. Rick has also rallied his own homeowners association, Villas of Holland, to adopt Paw Paw Park. He's personally recruited volunteers for several work days. He's brought a serious erosion issue on the MACC River to our attention. And additionally, he volunteers at parks throughout the county, including several work days with students. Rick also serves on the board of Friends of Ottawa County Parks, where he advocates for parks and other natural resources organizations within the community. Name a few. So as you can see, I think he's a deserving recipient. So please join me in thanking and congratulating Rick Bosch for his excellent service.
Always dangerous to give a PhD a microphone and say share a few words. Luckily, Kelly scheduled me right before the break, so you're okay. But no, thank you very much to the MACC Area Coordinating Council for this award. I really do appreciate it. It's also something, before I accepted it, I made sure that this was something that I'm being given for things that I'm doing and not for things that I'm done, because I really hope to continue to do this for many years in the future. And really last, this is one of these things where I'm doing things that I really enjoy, that I really feel are important. They're important to our community, and I get to do them with organizations that I really have a lot of respect for. And then last but not least, the people that I'm doing them with are people I enjoy spending time with. They're people that, I really consider to be friends. So this is something that I really do appreciate. So thank you very much.
Thank you, Rick. At this time, we're going to take our break. We'll reconvene at 11:20. Please visit the table, the food table. I think the red basket is the sweet, the green is the savory as far as bagels. You'll figure it out if I switch those around. We'll reconvene, like I said, at 11:20 and hear some updates on Project Clarity. Thank you.
I was under strict orders to be done by 11:30, so I'll talk fast. All right, good morning, everybody. My name is Dan Callum. I'm the Greenway Manager at the Outdoor Discovery Center, and I'm going to be giving a quick update on our project activities through Project Clarity in partnership with our project partners here. If I can get the slides to go. All right, so I represent the ODC network. We are the lead partner on our Project Clarity initiative, the effort to clean up and restore the MACC Watershed. The partners you see up here on the slides are invaluable to us accomplishing this work. Kelly and Rob at the MACC and all they do. Nice Water Environmental, who are our main restoration consultants, and then the Annis Water Resource Institute and Hope College, who assist in our monitoring efforts. So the quick summary of Project Clarity, kind of the why we've been doing this. It's been going on for, this is our 5th year of implementing projects. This was the result of community will to kind of clean up the lake and the rivers of the watershed. We put together a $12 million campaign and list of projects to begin to remediate water quality in the watershed by looking at land and restoration projects, implementing best management practices, doing education and outreach, and then maintaining projects that we've been able to put in. maybe. Yeah, too far. So part of the reason we have been putting in some of these projects is just dealing with area issues of sediment and nutrients running into our watershed, sources of sediment, all the research that was done. And now 5 years in, this is our map representing all the project locations and partners that we've been able to work with and put projects in. I didn't include this slide, but some of you may remember from our research in previous years kind of showing the priority areas where we want to work in, and we've been able to match the projects that we put in up with those priority areas where we want to work. So each of the spots on this map represent a partner who has been working with us to put in a project or practice at a specific site. And the next slide will have a lot of the work that Rob has been doing. So this represents the agricultural land, and this has mainly been our focus this past year, is putting in practices on farm fields. The yellow areas within our watershed are those that are currently being farmed or used for agricultural purposes, just slightly over half of the total land within the watershed. And the bright green parcels within that are parcels that have one or multiple best management practices on it. So as you can see, we've had a lot of success, especially down in the Overijssel and Fillmore Townships area. All told, we are at about 24,000 acres across the watershed that have had some sort of management practice put on that. So we're really happy with the progress we've been making. We've had some real traction this year with getting cover crops in. This is a radish down in Fillmore Township. We've had about 2,200 additional acres brand new gone in this year, including the acreage that have gone in from previous years and previous contracts, so 2,200 new acres. And we've also seen some new types of projects that we haven't seen before. So to summarize, we have seen a number of different projects go in this year, including waterways, gypsum applications, cover crops, residue management, and we also assisted in the purchase of a cover crop seeder for a farmer who farms about 500 acres in the Overijssel Township area. All told, we are over 100 projects that have been funded and approved through our agricultural committee since the project started about 4 years ago. And in total, we've got over 24,000 acres of BMPs that have gone in, representing just under a third of the available acreage in agricultural land in this area. And we've been excited to see a couple new things this year. I hope the suspense is building. So this looks kind of like a unspecial photo, but I know this is one of Rob's favorite photos that we've seen this year. This was one of our farmers who decided to plant his crop directly into a green standing cover crop. So on this field, you can see the rye that's kind of come up and sitting in the field, and he's actually planting a seed into it. So what this represents is basically a field that will have cover on it for 12 months of the year. Something green will be and growing on that. There aren't any months where there's just bare dirt on the field with a high risk of erosion. So this was a very cool thing to see. I think a lot of the farmers are interested to see how well this performs and if this is something that can be adopted broader. We've also seen several farmers who are using blends of cover crops. So not just one type of cover crop, but several different that have different nutrient benefits to them. So Rob's been doing some great work out there getting folks interested in trying some of these practices and projects. We did have our annual agricultural luncheon this past February. We had about 80 folks show up to it. Here's Rob giving an update to farmers on what we've been working on and kind of informing them some of the practices that we've been doing. The farmer we had present was named David Brandt. He farms down in central Ohio. He has a very unique cover crop system where he uses over a dozen different kinds of cover crops on his fields and talked to his farmers around here and kind of had them spur some ideas and thoughts on different types of cover crops and different benefits that come with them, and got some of the guys thinking. I don't think we've got anybody out using dozens of cover crops yet, but it was a good presentation and spurred some good conversation. All right, so we do have a few restoration projects that we're planning to get rolling out next spring. We did do a lot of the planning and permitting this year to kind of set these up. We do have a 319 grant from the DEQ to restore about 1,000 feet of Peters Creek in Zeeland Charter Township. So we've been out working with Nice Wander Surveying and getting the plan sets together. We hope to have our permits in hand yet this winter and be able to begin construction late spring. Dealing with, as you can see, some severe bank erosion, trees falling in, kind of a rough stretch of stream that's struggling with the hydrology that we're going to be able to fix. We did put in another 319 application. Kelly and Joe Bush did the heavy lifting on this project. Looking at about the last mile of stream located within the city of Holland and Holland Township on the north branch of the MACC River, which is our third highest priority. We're looking at some areas where we have some severe bank erosion, and again trying to fix and address some of these, create some water storage within the stream valley itself, hopefully minimize some of the erosion impacts and the sediment sources that we're seeing in these areas. So we've submitted that to the DEQ. We've got some positive comments back on the proposal so far, and we're hoping that gets funded this summer. One project that, and kind of one source of phosphorus that we've been trying to deal with for a number of years now is what do we do with phosphorus, particularly dissolved phosphorus. And this is a lot of times found in tile drains coming out of the edge of fields. And we were able to work with a couple partners and the Michigan Department of Agriculture and Rural Development to get a couple grants to put in these new filters, something that hasn't been done extensively in this state at all, certainly nothing in this area. These are basically a septic tank-like system that has iron slag put in it. And iron is able to bond to phosphorus very well. So basically by taking the water that's running out of a tile line at the end of a field, having the iron kind of filter out the phosphorus that's free floating, and then the water will flow into the nearby stream much cleaner. So we've got 2 grants from the Department of Agriculture and Rural Development to pilot these. We've got a farmer down in Overijssel Township who has some fields that he's willing to put these in. So we're going to install these potentially in the next few weeks here, if the weather holds, and kind of evaluate how efficient these are at removing the phosphorus and if these are indeed a cost-effective solution for dealing with the bioavailable phosphorus, which is a lot of time the key ingredient for some of the nuisance algae blooms we can see. We continue doing education work with various school groups around the community, getting folks out to some of our restoration sites, our mitigation bank in particular, getting school groups out there to work on hands-on projects. Our water festival was a big success again this past summer. Thanks to all our project partners who were there and the 3,000 people who came out to enjoy it. And we'll be back on Windmill Island again July 13th of 2019. And I did want to thank some of our volunteers, Rick among them, who have been helping with some of our lakefront monitoring. Maggie's going to get into much more detail on this, but the folks who are out on a weekly basis taking water clarity and water color samples for us, that are kind of helping to blend in some of the data between samplings that AWRI and HOPE are able to do. So we do have an army of volunteers out continuing to help keep an eye on conditions in the lake. So I believe that's about all I have. Does anybody have any questions on any of our project activities? Otherwise, I'll turn it over to Maggie.
I have a question.
Yeah.
Did you guys design that filtration system that you are implementing?
So the filter system is designed by a group out of the Detroit area. They have basically an industrial supplier who has leftover iron slag from other industrial processes. So they are working with a group out of Purdue University, actually, who put the design together. We basically give them the specs of the field, and they design and kind of tailor how big of a system to make for a given site. The life of the filter system, it's basically until the media gets used up, so they can tinker around a little bit with the type of slag they put in and the size. These will be designed to be roughly a 5 to 10 year span, depending on flow for water to go through. And at that point, they basically like a septic tank, you can take the top off the lid, kind of scoop out the used material and put new material in and have it continue to work.
Is there any benefit to recapturing the phosphorus in that process?
I think the company who provides the slag is interested in it, potentially to reuse that for fertilizers down the road, but I don't think locally we have any interest for it. We've certainly got plenty of phosphorus already.
What was the crop that the farmer put on that cover field?
That was corn. Soybeans. All right, thanks.
All right, I know I'm between you and freedom, so I'll try to be quick. I also wanted to joke that I should give you all a quiz because this is all in 2017 report that you all should have read, so if you answer the questions right, you get to leave, but that's not really going to happen. So I am Maggie Oudsma. Oops. I work at the Annis Water Resources Institute. I'm a technician in Al Steinman's lab, and so I do a lot of the field work that we do for Project Clarity, including we're going to be sampling some of those iron slag sites to see how well they perform. And like I said, I'm doing everything on 2017 because obviously we're in 2018 and my crew's sampling literally right now today. So we won't have that report until January or February next year, but it will be coming out soon. And so I'm going to go over just a kind of a snippet of all the work that we do. So we work in the tributaries around those remediated wetlands that were put in, as well as the effort that we do for Lake Macatawa itself and some of the extended research projects that we had going on in our lab as well. I think this needs new batteries. Okay. So for the tributary sampling, if you've seen my presentations before, this is no surprise, or if you've read the report, this should be no surprise. We do monthly sampling, so today is base flow, as well as we try to capture as many storm events as possible. We also have continuous monitoring, which ODC helps with, which stage and discharge. We also have turbidity sensors, which are that small probe at the bottom there that do continuous, and I'll kind of give you a snippet into 2019 that we kind of have a surprise for you. As well as we do general water quality sampling. So Paige here, who's a grad student in our lab, is actually using the larger YSI. It uses the same technology as that smaller turbidity sensor, but can measure a lot more activity. So it does temperature, turbidity, pH, even chlorophyll, and a few other general water quality parameters. We also do nutrient sampling, and so we do a water grab sample, which Lydia is holding one of our lovely white bottles to sample with. And we do this at the Hayworth property, although this map needs to be updated with that new construction on that road that's right next to it that happened there with a big culvert. But we have two sites upstream and downstream of the restored wetland area, which is that red area in the center of this map. And then we also have the Middle Macatawa property, similar kind of setup where you have that restored wetland area. And then we actually have two upstream sites. So one is on the main branch of the Macatawa River. The other is on Peters Creek, which is a main tributary into the Macatawa River just before that wetland. And then we have one downstream, which is on the main branch of the Macatawa River. So those turbidity sensors that I told you about are actually located on this or on these sites, just on the upstream and downstream of the main branch of the Macatawa River. And I'll kind of go quickly through, there we go. So before I get into the actual results, I just kind of want to orientate you on this graph so you're not trying to look at everything all at once. So along the left-hand side, you have turbidity in NTU, and that's basically how it measures light at 90 degrees from the probe. Along the bottom, you have years, and this goes up to 2017, and I'll show you actual 2017 a little bit here. But you have time along the bottom. On the right-hand side, you have total rainfall in inches, and this is actually an inverse axis, and so the bars are actually going to come down from the top for that. The vertical bar, or the vertical dotted line in the center, is when the wetlands were restored, and so anything to the left of that is pre-restoration, anything to the right of that is post-restoration. And so if we just look at pre-restoration data, you'll notice that the dark bars, which is the downstream site, and the light lines here is the upstream, they're pretty much follow in sync with each other. So if we look at just post, or just after the wetlands were restored, you notice those green, the dark green is very, very low compared to the upland. So, we're like, sweet, those wetlands worked. And it gets a little bit more muddled as we move into 2017. But again, we're looking at different rainfall rates and that sort of thing. I mean, the wetland's still getting established with plants. It's fairly relatively new. I mean, most wetlands are, geologically been there forever. And so this is only a wetland that's a year old. So this is not really surprising in that regard. So we're going to change a little bit of our scales here. So this is just showing 2017 now. And it's a little, again, it's not the easiest thing to read ever, and I understand that, but really it's kind of showing the same as 2016 in regards to that there is some reduction from the upstream to downstream, but not really as significantly as we saw right afterwards, and that could be due to the rainfall that we had last year. All right, so back to Middle MACC, and we're going to look at all 3 sites now, and I'm just going to show you total phosphorus for these 3 sites. The Hayworth property showed similar results, but just for time's sake, I'll kind of save you some of the repeat information. So this is taking an average for the entire year at the Middle Macatawa sites. So the upstreams are bars. Oh, I'm losing my mic. Are the 2 bars on the left, and then the downstream is on the right. And they're all significantly different from each other, so that's what the letters stand for there. And then this is in total phosphorus in micrograms per liter. The red line is that total daily maximum load, or that TMDL, of 50 micrograms per liter. So during base flow condition, this is fine. This meets the requirements of the watershed, and so we're happy with that. However, when you take into storm sampling that we have done, and this isn't capturing all storms that happen, this is just the ones that we captured throughout the year, it is significantly higher than that 50 micrograms per liter. I mean, we're talking about over 1,000 micrograms a liter of total phosphorus, which this should not be news to any of you that Macatawa has too much phosphorus in its system. So we can't really say how well the wetlands are working because the whole system is too overloaded with total phosphorus that we can say what the wetlands can't even take care of it type of thing. That's okay. So what does this all mean for Lake Macatawa? So we sample Lake Macatawa a little bit different frequently. We do spring, summer, and fall. Similar general water quality sampling with the sonde. We also add secudus depth, so we are like the citizen scientists out there, but we're doing it in the middle of the lake instead of on the edges. And then we also do nutrient sampling, and I'll show you again total phosphorus and a little bit of chlorophyll A, which is a surrogate to algae measurements. So these are our sampling locations within Lake MACC, so we're all kind of throughout the lake itself. And then we take the bottom 3, so that's showing the eastern, central, and western basin of Lake MACC. And we do that for an average of the year to create a water quality dashboard, which is a little bit more of a kind of digestible form of all the information that we gather. So this is what the dashboard looks like. The green is showing the desirable range, the yellow is meeting the goal, and then the red would be exceeding the goal that was set up for different parameters. For total phosphorus, meeting the goal would be anything below 25, the desirable range is anything below 25. Meeting the goal is 25 to 50, and anything above 50 is undesirable or over the 50 micrograms per liter of that TMDL. And so as you can see, we're definitely way above our 50 micrograms per liter for an average of the year, and this is no surprise. This also shows historically where we've been and where we're going. And so you kind of could see a downtrend. Starting in 2015, we had a little bit of an uptick. But Lake Macatawa responds on geological time. So this is really showing more natural variation than all the BMPs that have been put into the watershed. So again, not a surprise really, we just kind of have to wait and see, which I know is really hard when you invest so much time and effort into a watershed. I hate to be the gloom and doom slightly. So we also looked at, does rainfall involve anything? Because we saw, the storm events had really high total phosphorus. When we sample the lake, it's not necessarily after a storm event in that regard. But as you can see, the gray bars, which have been added to this graph, really show no correlation into how much total phosphorus is in that average. So there's really no correlation there. This is showing chlorophyll, which again is a surrogate for how much algae is in there. Similar color scheme, just different scales. So anything below 10 micrograms per liter is desirable, 10 to 20 is meeting the goal, and anything above 20 is exceeding that goal. So in 2017, we were just above 60 micrograms per liter. And then if you look at the historical range, we're really showing, again, natural variation. It's not really outside the norm of Lake Mac in that regard. And then quickly, the last thing is Secchi disk depth, and so this is actually an inverse, so we're going for how clear the lake water is. And so you put in that black and white disk, see how clear it is, so the shallower it is, the less desirable it is. So anything below a meter is undesirable, a meter to 2 meter is meeting the goal, and anything above 2 meters would be desirable. And so we were about at a half a meter, which as you can see historically is not outside the norm of Lake Macatawa by any means. So it would be really nice if we can start seeing some of these increase to actually reaching towards our meeting our goal for the lake. And so just to summarize that really quick, no surprise, phosphorus is way above that TMDL. And really, and I know Dan, of course, is working on many, many projects as well as the MACC on doing more implementations of BMPs, and that just needs to continue. We're treating, as Dan mentioned, some of the tile drain issues that are occurring. And so it'll be kind of interesting to see where things go from here. And we'll continue to monitor the efforts being made in Macatawa Watershed. So we're going to switch gears a little bit away from water quality and actually go into fish monitoring. So it's in 4 locations in the lake, and they're fairly close to our water monitoring locations. We do fyke nets as well as boat electrofishing. Fyke nets are set for about 25 hours. Boat electrofishing is done at night, and they're in 10-minute transects. And so let's see what we caught. So first, here, I'll just show you what the fyke nets look like in case you're not aware. They're set in 3s at all sites. 2 are set parallel to the shore, and 1 is set perpendicular, and this is a passive sampling effort. So the fish basically hit our nets, swim into the mouth, and it has a really hard time swimming back out. We identify the fish to species as well as take a total length on all of them. Like I said, boat electrofishing is done at night, so an electrical current is put into the water, stuns the fish, easily capture them, they come to. It's a lot less severe than even hook, line, and sinker kind of type of catching. They come to, we identify them and release them back into the watershed. And so this is our results, and I'll say how many fish we caught, and you're gonna be like, how does that math add up? So we caught over 6,500 fish, and you're going, that doesn't add up, because that's less than 1,000 there, or right around 1,000. In one of our nets, we caught these brook silversides, which looks like this. They're a very small fish, only a couple inches long. Pretty much a lot of other fish like to eat these. It's not something you typically catch on your line. But we caught over 5,000 of them in one net. It was just a ball of fish when we pulled it up. It was ridiculous. So we had to exclude that from our analysis just because it skewed everything way off to the side. But as you can see, we still caught a lot in our fyke nets regardless. But we caught yellow perch, bluegill, kind of the typical things that you would see that make up the most of our catch. Some of the interesting things you see, so I normally love to do cool fish photos, is we caught a beautiful brown trout, which we were pretty surprised to see in Lake Macatawa. Normally they're smart enough not to swim into our nets, but we were really surprised on this, and we did release it, even though we all wanted to keep it, because I'm sure it would have been delicious. But the other interesting thing we caught in electrofishing was a giant goldfish. So we know this was recently released, so when people release goldfish into the lakes, they typically turn brown where you don't really notice that they're a goldfish. This was someone's pet in an aquarium that someone decided to stick into Lake Macatawa, which we were pretty surprised about. We did not catch it this year, so in 2018, but you might want to put a public service notice out of don't put your aquarium in Lake Macatawa. It's kind of wearing a neon vest, which I'm sure some fish probably gobbled that thing up in no time whatsoever. So that was pretty interesting. So the other projects that we have going on, like Dan mentioned, the Citizen Scientist Report, I'll talk about that, as well as the SWOT modeling. And I'll explain more what SWOT is in a minute. So for Citizen Scientists in 2017, there was 20 citizens that worked on this at 11 different sites throughout Macatawa, as well as a little bit up the main branch of the Macatawa River. And I know people from the MACC also helped. They measured water clarity, with a Secchi disc, as well as we gave them this Farrell-Uli color scale. This color scale was made basically from blue is 1, and then 21 is almost like a Coca-Cola brown and everything in between. And this kind of has been used historically, since like the 1900s to kind of evaluate water quality and that sort of thing. And so this is what the results looked like. So the Farrell-Uli scale is along the bottom. So again, 1 is that crystal clear kind of blue water. 21 will be the Coca-Cola brown. And then you have your Secchi disc depth inversely. So 0 is on top, 160 is on the bottom. And so that's kind of all the sampling that was done on a weekly basis in Lake MACC with all sites. And really what we found was that the darker the water, the less depth you had in your Secchi disk depth, which I'm sure we all can relate to of brown, muddy water in Lake Macatawa. You really can't see through it, which is no surprise. So I'm pretty sure that's probably the trend we'll see this year or in 2018 from the efforts, but it'll be interesting to see how this kind of continues in this trend. So SWOT actually stands for Soil and Water Assessment Tool, which I do not run. We had a postdoc in our lab, Lydia, who ran this, so I'm slightly talking out of my element, but I'll do my best. But when you think of SWOT, of course, you think of this. And I can promise you we are not sending police officers out in the Macatawa watershed to do sampling for us. What it really does is a bunch of different things. So it's a model that you can use to evaluate climate, land use, management practices, all into one. So it's used mainly in agriculture, which we know we have in the Macatawa watershed, but you can also use it for urban developments and that sort of thing. It can help decisions by playing these what-if scenarios. So if you want to implement a BMP in one area but don't want to have to spend money on it to see if it works, you can kind of play it through this model to see how much the benefit would be to the watershed and water quality. There we go. It takes a whole host of input as far as runoff to TMDL, so that total daily maximum load, to the best management practices, to sediment quantities, everything that you could possibly imagine. It's kind of a complicated model. Again, I'm talking out of my element, but you get really cool maps like this. So this is preliminary results, and this is showing total phosphorus in surface runoff as well as in the sediment runoff as well. And you can see, based on Dan's map, it's in those hot zones, so that red area is where you have kind of where all the phosphorus is coming from. And so you know, based on this model, that's where you should focus a lot of your best management practices. All right, so here's my teaser for 2019, so it'll keep you coming back and listening to me, I promise. So those turbidity sensors that we have set out, so this is what they look like in the stream. Twist Think actually approached, I believe, ODC, as they wanted a project for one of their interns, and they're making it so we can have these turbidity sensors actually have live data. So just like you would pull up a weather station, you could actually pull up a turbidity sensor. We only have 2 right now, but potentially more. You could pull up a turbidity sensor and see what the rivers are like in the stream. So again, I did not create this, but through the magic of computer science, they can create this really cool dashboard that you'll be able to pull up, which I'll give you a little bit more information than just turbidity itself. It'll give you discharge as far as like what the USGS gauge is, as well as precipitation that day. So our turbidity sensors log every half hour, and so pretty much it'll update itself automatically, so you can see what's happening in the watershed as well. And with that, I'd like to acknowledge, of course, everybody here that has worked on Project Clarity, including the staff that isn't here from my institute at the Grand Valley State University. And with that, I'll take any questions. You probably don't have any, because like I said, you should have read this all. Yes?
There's only one flow meter, and
yes.
Is that an issue for you, or is it something where fall is?
Yeah. So he's talking about the USGS gauge. There's only one in Lake Macatawa because it is a relatively small watershed. Bigger watersheds typically have more, but because Macatawa is so small, that's kind of why they have one to cover the whole area. It's a little bit of an issue, but we also have transducers that we put out at all our sites exactly, and so we can model that flow there. So we've taken measurements and have a model. Yeah. I mean, USGS would be great because they sample a lot more than us and they have experts on it. Not that we're not experts in our own right, but it's kind of something they specialize in. It's not too much of an issue because, every site that we go to is a little bit different in regards to that, but we also could tie it to the USGS gauge if we needed to kind of supplement our modeling. Again, SWOT model probably could work wonders, or a different kind of model could work wonders on that regard. So it's not too much of a hindrance for us, at least. Any other ones? Yeah.
I had a question. You showed the hot zones
Mm-hmm.
to the south that correlated with the agricultural practices that are being managed.
Mm-hmm.
But we're not seeing any significant changes in the lake. So expectations on
Yeah, so
time we have to expect
right. So
seeing results.
So she was asking of, showing the hotspots from the SWOT model to where Dan's doing all his BMPs and kind of where the expectations should be. And this is kind of where I have to reiterate that, landscapes work on geological time, which is not necessarily even in our lifetimes, which is unfortunate. So I like to compare it to going on a diet. So even though you want the pounds to melt off instantaneously, it takes maybe a year, maybe 5 years to get to that goal weight. Where this might be, maybe it'll take I don't want to say an exact year amount, but maybe it'll take longer time than just, you put the BMPs in the next year, you all of a sudden hit that magical number and you see a reduction. So.
But would your expectation of BMPs be that within a decade we begin to see some?
You should in most, depending on all the factors that get put into play of, climate change also comes into play of how much rainfall and that sort of thing.
It's going to be hard to continue to convince people to change.
Right. And that's why we're very cautious of what we say in regards to, we don't want to discourage because best management practices are very important. And improving your watershed is extremely important. And this is just going to become more of an issue as we have drinking water issues, as PFAS gets more and more into the news and that sort of thing. Not that we sample for PFAS in Lake MACC yet. But, this is going to become more and more important. I think as a society, we need to realize that it might not be in your time frame as far as the life that you live that you see the benefits that you put into place, but kind of the future generations. You're welcome. But yeah, try not to be discouraged. Yes.
Do we have a phosphorus budget for Lake MACC?
There is a phosphorus budget for Lake Macatawa. So that's at that 50 micrograms per liter. And so all the best management practices are trying to get to that 50 micrograms per liter as a lake average. I know there's been internal loading work. It wasn't done by us necessarily. No, maybe. I don't know. I don't know internal loading. I mean, the sampling that we're doing is more kind of the external loading. I mean, we're focused on those restoration areas for the wetlands in particular. But you can kind of extrapolate that out a little bit to the watershed as far as, we're capturing everything above those sites. So there's a lot of external loading happening, and that's not surprising with all the agricultural fields that are out there. Not that I'm blaming the farmers by any means, they need to make a living too, but I don't know what the internal loading would be. On the fact that Lake Macatawa gets dredged a lot too, just because it fills up with so much sediment, I don't know how much there would really be as far as that goes, but that would be something that potentially could be looked into. Does that answer your question? Yeah. Kind of, yeah. Yeah.
Since you mentioned the periodic dredging in Lake Macatawa,
Yes.
the internal part, right?
Yep. Yep.
This year, those who saw the core out there, they had their hydraulic dredging operation this summer. And the sediment that came into the dredge site up at Lakewood this year, I've never seen so much sand go in. Something changed, I don't know what. But there's a lot of sand in there that everybody's fighting over at the moment.
Right.
Usually, you get some sand a little bit where the intake pipe drops it into the basin there.
Yeah.
But this was almost all through it, just a lot. So I don't know if maybe we're seeing some changes in what's coming in.
That's very well possible. Yeah, we don't test the sediment in the lake itself when we do our monitoring, so it's not like we take sediment cores so we really know what's going on. And of course, we're not involved with the dredging, but that is interesting that you can notice that it's more sand than probably the muck that everyone is familiar with for Lake MACC. So yeah, there might be benefits and changes that are being shown that we're just not seeing because of what we're measuring as well. So yeah.
You were talking about not seeing a change as much as you'd like, but in some regards we are seeing, because with growth, development, you're not seeing it go higher.
Right. Right. I mean, historically, it has been by far worse in a lot of different samplings. Like total phosphorus has been way higher than what we've seen. It's just not that reduction that a lot of people want to see, where you kind of going into that more for our dashboard into that yellow and green zone type of thing. So we're kind of maintaining at the moment, which is good. Maintaining's good, but we just kind of want to see that, start seeing that drop off hopefully soon. Yeah, Dan. Go for it.
2017, almost twice the amount of rain that we saw in any previous year we sampled.
Yeah.
And we didn't see the bar go all the way off the graph, so I'd say that's encouraging.
That is. Yeah, 2017 was definitely a challenging year trying to get base flow in with all those storms that came through. This year we had definitely, in 2018, we definitely had a dry summer compared to the spring and even the fall / now winter. Even though we don't have snow, it's been raining more than anything. So that'll also come into play as far as how things move forward. That it's, you almost can't totally directly compare year to year because of the difference that we're seeing in the climate and the rainfall and everything. Yeah.
You talked about agricultural runoff. Is there a comparable study or emphasis on lawns?
There has been. We haven't looked at it directly for like MACC or anything like that. I know that the MACC has lawn people that sign up for, basically not putting phosphorus on the lawns within the Macatawa watershed. But we haven't looked at any study directly in that regard, but I know they're out there. Anything else? All right. Thank you so much.
Thank you, Maggie. Thank you, Dan. So that's the end of our agenda. I want to thank you all for coming. If you haven't signed in or signed up to be on our distribution list, please do so. It's in the MACC so that you can get information about events or activities and updates. But I want to thank you all for spending your time with us and your interest in the watershed. As a parting gift, we have some to-go bags on the bagel table that Kelly thought ahead to bring, so please help yourself to those. But thanks again for coming and have a great rest of your day.